free in there. So maybe not for carbonation, but it is a possibility because yes, it takes some calcium hydroxide, but mostly it'll fill the pores. Most of the products are non-reactive. It does reduce the diffusion. It does reduce the flow of CO2, which has better effect. So you need to take a balance act. Everything in concrete technology is about a balance. You cannot have perfect concrete without consequences. But that's okay. As long as you're aware of it, you'll do fine. Every material has weakness, including steel. So are we clear with carbonation? Just the background of it. I will rely on these slides and your knowledge later on to do mathematical work. So coming to chlorides, I absolutely love chlorides. Part of the reason is that's... Oh. It's just the expansion part of it actually. So the more calcium hydroxide you form, so assume you have pore structures here. 2 tubes represents the pores. So you have calcium carbonate forming in one of them, so there's a bit of expansion in that. But that's okay. It put a crack to the next pore and it connected that, and then it released that expansion force. Good. But then you have calcium carbonate forming in the next one, and has nowhere else to go. So it then will have to go outwards. So all these micro cracks that you see in concrete eventually might lead to a macro crack. We call it spalling, whether it's popping or spalling. So when you get spalling, that means that steel is now exposed to the external environments. By then the damage is already done anyway. So do you want to say anything further on that? Okay. So going back to chlorides, I was saying that I love chlorides. Why do I love chlorides? What's my love with chlorides? It keeps me in job. Absolutely, because the fact UK relies on chlorides, it keeps me in job. I'm one of the go-to persons in the UK for anything new with chlorides. And if they stop putting salt in the structures, then I'm in trouble. And so I presume a lot of you will start to work in chlorides one day or another. It's an omnipresent thing. Does chlorides only affect concrete, or does it affect anything else? Does it affect steel? Yes. If you look at cast iron pipes, water pipes, put in the soil for drinking water, when we were looking at the cross-section image of it using backscattered electron microscope, we were looking to see what way the cast iron was made, whether it's spun or I don't know the other method. Anyway, spun means you will see the inclusions in a particular nature, particular way. We could even spot chlorides in that. So chlorides can even go through the cast iron. It's as small and as annoying as that. And it goes in the cast iron, it goes in and corrodes all the carbon deposits it have in the graphite, and that's enough to keep spalling them. Same as chloride in concrete. But the best thing about concrete is concrete doesn't mind chlorides. It has nothing to do with chlorides. It comes in, it reacts with concrete. It still is a good reaction, is a good relationship between the two. So there's nothing in chloride that will affect the concrete. It's not the concrete the problem. The problem is the steel within does not like chlorides. So same mechanism here. It's the number of chlorides on the outside and the lack of chlorides on the inside creates a concentration gradient. It's that driving force. It pushes the chlorides in, and the chlorides will start to react with some of the phases. What we know is it will react with calcium aluminate hydrate and it forms Friedel salt. We're also now nearly agreeing that it will react with, or will be combined with, calcium silicate hydrate in a more physically absorbed form, not a chemically bound form. So the more calcium silicate hydrate and the more calcium aluminate you have, the better its capacity to hold chlorides. Aluminates are great in the sense it's chemically converting it, so it's a more stable compound. So if for a chlorid environment you will prefer to use more aluminate cement, which of your byproducts have more aluminate? Microsilica, PFA, GGBS. Which one has more aluminates? Therefore ideal for this environment. Have you seen the oxide composition of cements or materials? Which is where they would list saying calcium oxide, silicon oxide, aluminum oxide, oxides after oxides after oxides. That table is very important. Fly ash. Your fly ash has about, typically maybe about 12 to 24 or 28% aluminates. I don't know what you get here, but we get something close to 21 percentage of aluminates in the fly ash. So including more fly ash means you put more aluminates in here. But it has its own issues because I don't know the fly ash that you get here. Some fly ash are very reactive. The fly ash that we get, therefore the coal that we get is from Russia. They're not really that reactive. They're very dormant fly ash. So we can afford to add a lot more because you don't get that spike of reaction. But we also have the problem that it won't set for the strength development will be very slow. So not ideal. You need to be really carefully planning them. But nevertheless, I like that aluminate phase. So if I had the freedom to select a material, I would have just taken all the materials together and take all the minerals that I want and engineer what I need. And when I say that, I'm really not far from doing that. You know about the blended cements. You now have, I think most of the cements in India probably is blended already. So you have PC, Portland cement, Portlandite part of it. And then you have the additives, whether it's PFA or microsilica, rice husk ash, which is microsilica, or GGBS. Yeah. So that's double blended, binary. And have you heard of cements that can have 3 parts to it? So PC, PFA, microsilica. But that's not what you buy in the bag, isn't it? You blend it, am I right? Okay. Is it practiced or is it just in the research sector? Research sector. Is it practiced, these triple blends? But do they already make structures out of the triple blends like PC fly ash, silica fume, or PC fly ash, something else in the outside world? Okay. Because they need to have the capability to blend it. And in the lab it's easy. A person can blend it, but not in the commercial scale. It's really... Inside you do that, okay. If you can get them in hoppers, yes, you can do that. So that's an investment, isn't it? You have to get a hopper installed. Right. Is it a powder that you get or a slurry, microsilica? Okay. Because if silica have a health issue in the UK, they prefer slurry. So it's just a liquid form. 50% silica, microsilica, and 50% water. So we adjust that with the mixing water. Anyway, but that means it's not too far. Meaning you're already practicing it. Not possibly viable for every structure, probably for very typical structures. And that's where the structural construction will need to be looked at. If it's precast and everything is made in a yard, they can blend anything they want. Majority of the precast in the UK use a lot of limestone fillers. Not because they have a lot of limestone, it's because it's inert. And they can control therefore the reaction and the rate of reaction. And also they're using it for a different purpose, to make it flow, SEC, self-compacting. Sorry, deviating back to chlorides. So I need the aluminate phase, I need the silicate phase, and I need any other phase that I want to form the structure. It again is a two-part thing. There's a transport controlled by the concentration difference and the gradient diffusion, and there's a reaction phase. Okay? Chlorides are quite difficult to model. They are mathematically challenging to model, but it's not impossible. And when it forms calcium chloroaluminate, which is the Friedel salt layers. And if it manages to exceed a certain value of chlorides that the chemistry can balance, called as chloride threshold, it will then destroy the passive layer of steel. Okay. Bear in mind, I said to you that it can even go into cast iron, which means it can go and attack steel quite easily. Okay. So once the protective layer is gone, then rusting will form. And annoyingly for chloride, the rusting could be in a very minute location, and it can come out of the equation all the time, which means it's a catalyst. So it can just keep coming back and doing the damage as long as it has other factors to fuel it. Okay? Structurally speaking, if the integrity of the steel, so for structural engineers, we know that if the steel is damaged, if the amount of corrosion in a steel can be quantified, let's say somehow, what's more critical for us is not the surface damage. What's very critical for us is the extent of damage on one particular location of steel. It's the area of cross-section of steel. So the problem with chlorides is that it's pitting corrosion. Very typically it pits the steel. So pitting refers to, so if you have a steel surface like that, and if you lose a portion, won't be uneven, that means the area of cross-section available to carry the loading is confined. Some may argue that this portion can take the loading, some may not, depends on what kind of loading. But, which means your cross-section is reducing tremendously. You do have safety net in your structures. What's the maximum loading for steel that you're allowed to put onto the steel structure or the steel reinforcement? Would you put 100% capacity as loading? Well, we'll never do that. What's the maximum we can go? Factor of safety, that's the question essentially. So factor of safety for steel is, I don't know if that's the factor of safety symbol here, but yes. For steel? For concrete, we use 1.5 for new structures, and for retrofit renovation kind of work, we use 1.2. That structure is already existing. For steel is the question. In the UK, because it's a very controlled production system, they can guarantee to a large extent that the number of defects would be very, 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 very low. Which means you only have 15% extra in the steel. So 15% area reduction could be as simple as that. Okay? But we never put the loading as high as that anyway. I mean, if you look at structural codes, you will see the amount of factor of safeties you have brings you down to loading net effect of 33 to 35% of the actual capacity of the structure. So there's a lot of redundancy. Problem with the chlorides is that redundancy doesn't matter to it. It can go and attack one particular steel and can just kill it. And that's enough for the structure to collapse. So that's with chlorides. Anything else I haven't said about chlorides? So if you summarize it, what are the controlling forces that you can change to make concrete good in this environment? Primary is diffusion. Control the diffusion, control the rate of flow, you control everything thereafter. Because rate of flow is controlling the reaction anyway. If the rate of flow is low, then the reaction will be enough and sufficient to get rid of all the chlorides. So that's your primary goal, control the diffusion. What else? give it a chance to have more reaction. I'll come to you. Give it a chance to have more reaction means you add more minerals that will react. Increase the aluminate phase, increase the calcium silicate hydrate. There are two kinds of calcium silicate hydrate. If you use GGBS, you get a secondary calcium. So those are the other thing. What other choice you have? Good, yeah. Consider anything other than steel. That's the ultimate game. But you can put a protective layer either in the concrete itself or on the steel. You've had a number of protective layers in the industry. I think India is one of the leading chemically activated systems provider. So protective layer can be just an oxide coating, might do the job. Could be epoxy, could be a number of things. I don't know what's available in the industry now. What other choice you have? When do you apply the protective coating? Is it on? When do you apply the protective coating? Is it epoxy coated bars that you can buy, or is it just on site that you can spray something? Okay. Both are true. You can spray the stuff as well. What else can we do? Coating on the surface. Yeah. If you happen to be the unfortunate owner of a structure where the diffusion is low, remember diffusion is driven by the concentration difference, right? Keep that concentration away from you. So if you were to provide a coating, whether that's tiles or